Just to confirm, is everything working on my side? Sound and screen sharing?
Yes, yes.
Okay. So this will be a short overview of quantum computing. Not go into the technical, but rather we will see the motivation behind quantum computing and where the field is going and how it's being developed at the moment. Let's start by making a small comparison between what I call the classical and quantum worlds, but through, or let's say, from a computing aspect. So generally, we're all using computers right now to follow rather live or the recording, but generally we perform classical computations in the system. So I will introduce the term classical. By classical, what I mean is that making this distinction between what works with classical physics and what works with quantum physics. So our computers, everything that most things that we know are called classical. So in the classical computations, we generally use the binary systems. So we will use bits, zeros or ones, and the zeros and ones are the unit of information in classical computation. Classical computing is based on classical physics. So in classical physics, it's basically the one that we learn in high school, and then we keep using in various fields of technologies. We have some properties like positions being well-defined. Some particle has a well-defined position x. Same goes for bits. They have a well-defined value, either 0 or 1. Now, these properties, they are enough to make any sort of computation. Okay, classical computers are completely equivalent to computers, but they do not operate in the same way. Now, since they do not operate in the same way, they are based on classical physics. Simulating the quantum nature of the world becomes very difficult, and this has been known already and discussed. And here's a screenshot on the right, a paper by Richard Feynman, Nobel Prize in Physics, where he was talking about quantum mechanical computers, that is, computers that use quantum mechanics to simulate quantum mechanical systems. And this was in 1986. Feynman is, let's say, widely known to be one of the fathers of quantum computing. So it's not a very, very recent field of science. Now, as I said, since nature is quantum, we use quantum computers to efficiently simulate it. So we need a shift from to qubits, so from classical bits to quantum bits. Classical bits, we write them as zeros and ones. Qubits, you see this notation here. This is called the ket. It's a vector, but it's not very important at the moment. Just keep in mind that whenever you see these notations, these you can translate directly to this ket 0 to 0 and this ket 1 to 1. Now, qubits, they obey quantum mechanics, as we said. So they can have quantum mechanical properties, one of which is superposition. So qubits, since they have basis states 0 and 1, they can be either 0 or 1, but they can also be in a superposition of these two states. And the superposition is written like this. So this is something you will not see in classical computers. You will not see a bit being equal to 0 and 1 with some probabilities. And speaking of probabilities, these A and B factors here are for this in qubits, they are complex values. But again, this is not the main point of the talk. The main, let's say, the main idea behind these A and B is that they give us the probabilities of measuring a qubit, which is initially in a superposition of 0 or 1, to be either 0 or 1. The procedure is very simple. Just take this coefficient and take the square of its module, and this gives you the probability. For instance, here 0, and then with B it gives us the probability for 1. So just to summarize, a qubit can be in a superposition of two states, but once you measure it, once you see it, try to read its content, it will collapse to either 0 or 1. and it will collapse to either 0 or 1 by some probability that is defined by A and B. The second thing that is unique to quantum mechanics and quantum computers by extension is entanglement. Now, superposition, we can have that classically, it's not a problem. I don't know if you have seen these Starlink satellites, have antennas which are flat, and the way that they direct their beams is through something called phased array, and this uses superposition. It's not quantum superposition, it's just classical superposition of electromagnetic waves, and it's useful classically. But this is something that is not we do not see classically. That's entanglement. Let's say we have two qubits, which I called here Q1 and Q2. I can set them up such that they're always the inverse of each other. So if one is 0, the other is 1, and vice versa. And we can do this with no extra work. We can do this, and they will keep track, or they will remember their interaction of how they were without extra work from us. So the state that I was describing is written as such. Q1, Q2 is equal to the sum of 0, 1, and 1, 0. What this means is that this Q1, Q2, this describes both qubits, and it's in a superposition state of either being one of them being 0, the other being 1, or vice versa. And if you go back here, we said that they can be in superposition state, but when you measure them, they have to collapse. Here they have to collapse to either 0, 1 or 1. So they keep their entanglement, their correlation. We can do this classically, but classically we need some extra program to keep track, saying that, okay, I measured qubit 1 to be 0, set the other one to 2, and that's an extra computation. In quantum mechanics, this is inherent. This is an inherent property of quantum mechanics. Now, let's just summarize in the last 3 or 4 slides in this slide called classical versus quantum. So bits follow the rules of classical physics. Qubits follow the rules of quantum physics. The state of a bit is always either 1 or 0. A qubit, in addition to being either 1 or 0, can also be a superposition of both. 1 or 0. Sorry? Okay, so someone has unmuted themselves.
I think it's Nada. She should cut her mic. We're hearing too much noise from her side.
Yeah. Okay, I'm not seeing the team, so I'm just seeing the slides. I guess the issue is resolved. So let me just let me just go back. So bits follow the rules of classical physics. Qubits follow the rules of quantum physics. This is the fundamental difference. Bits either in 0 or 1. Qubits, they can be 0 or 1, but they can also be in superposition of both. But the main difference that really makes the whole quantum computing thing lies in entanglement. Qubits can inherently be correlated. So they do not need someone to keep track of all the correlations like for classical bits. And this is where all the quantum advantage will come from. Now, we briefly described the difference between a classical bit and a bit. Really, this is the only difference is that one obeys the classical physics, the other quantum physics. But the question is, why do we need quantum computing? Now, the first answer to that was already presented in the first slide, was that nature is quantum. So if you want to simulate nature, we better have a quantum system to simulate it. If we use a classical system, it's possible on paper to simulate it, but we will need too many steps, too many time resources and space resources to simulate nature, or the quantum nature of our universe. You can actually see here on the right a graph that shows the difference between simulating a quantum system with a classical computer and with a quantum computer. Now, because of all of these interactions, because of all the entanglement, the problem, or as our system grows in size, the computation time, or actually all computation resources, they grow exponentially. So if we had interacting particles that are quantum, we would, and let's say also that they are qubits, just to simplify, so they have only values between 0 and 1. Then for these n particles, we would need n computations of the correlations, and we would need, 2 to the n computations, and also 2 to the n states that we need to store. So this is an exponential growth. In quantum computers, they do not need to keep track of the correlations. They are already inherently entangled. So if you have n particles, you need, as a lower bound, n qubits. And we can see this in this graph. The classical computer complexity will grow exponentially, as the quantum complexity at best will be constant, but in general it's either linear or polynomial. And we can also see something here that I've drawn on purpose. At the very start, so when the problem size is small, we have some overhead for quantum computation, because it's not easy to perform quantum computation. But as the problem starts to get more and more complicated, quantum computers will perform better than classical computers. So the first answer was that nature is quantum, we need quantum computers. Second answer is more practical. We need to simulate quantum systems in real life. So for example, molecules and materials at the quantum level. By molecules, I mean big molecules. Take, for example, protein. You can simulate it classically, but it would take millions of years for your simulation to be done. So what we do is that we make approximations and we lose accuracy. Say for materials, like we want to create some sort of material with properties. If you want to simulate it at the quantum level where these properties are important, you need a quantum computer. There is another reason why we also need quantum computers, is that this superposition and entanglement properties of qubits, they can be leveraged for other kinds of computations. And I've chosen here an example, which is breaking some cryptographic systems, and with an accent here on some, on some, so not all. We do know of an algorithm that breaks the RSA cryptography algorithm. It's called the Shor's algorithm. It does not break other cryptography schemes, but it does break the RSA algorithm. And I've chosen this example just to showcase that it's not only about science and simulating the universe and creating some new materials and maybe, I don't know, discovering interesting drugs, or I don't know, diseases through understanding how proteins work, etc. It can also be a question of national security. So if you have a nation that can break cryptographic systems, well, you need to step up your game. Now, a little bit more practical, not problem, but something that you can relate to. I'm going to two problems that can be solved using quantum computers. The first of which is the traveling salesman problem. So you can see here on the right a map of Slovakia. Let's say has a truck or a fleet of trucks that start at Bratislava, and they want to visit several cities delivering goods and maybe also loading some goods. And you want to visit all of the cities and go back to Bratislava in the least amount of time. So you want to take this translates to the shortest road, and you also want to visit these cities exactly once, because once you service them, there's no need to go back there again. This is the traveling salesman problem, very important and central problem in logistics. And well, the problem definition I just stated was the shortest path that visits n locations exactly once and then returns to the initial starting point. If we were to solve this with classical computers, this gets out of quickly. For I don't know how many, I don't know what the cutoff is, I don't remember the numbers, but let's say you have 100 cities and you want to service them. Finding the perfect solution is, again, on paper possible using classical computer, but it would take, I don't know, maybe a couple million years, and we don't live that long. So this is what we call a classically intractable problem. Quantum computers, we do have algorithms that can solve these kind of. So it's an important problem to solve in logistics, and by solving this problem, it's not just a mathematical problem that we're trying to solve here. Solving this problem means we reduce travel time for our. We reduce energy consumption, so we can consume less fuel, and ultimately we save money. And quantum computing, in this case, actually helps us solve many problems at a time. For example, I don't know, energy consumption and CO2 emissions, and at the end of the day, saves us a lot of money. The other application of quantum computing, which is maybe a bit more, I don't want to say interesting, but we're closer to do it than solving the traveling sensible problem, is quantum chemistry. And quantum computing can be applied to a bunch of problems in quantum chemistry. Here I've taken this picture. This is from last year's Deloitte's Quantum Climate Challenge. So what they do is that they have this filter here. So it's a very molecule. It's made of magnesium, manganese, oxygen, carbon, and hydrogen. And its job is to filter for CO2 molecules. So if you look here at the zoomed out region, you can see a CO2 here molecule, and we want to see how well it bonds to this filter. Now, why are we interested in such a problem? Well, to simulate it, it's a nightmare. We have thousands of molecules, tens or hundreds of thousands of electrons, and in chemistry, it's the electrons that perform, let's say, that are important in the reactions. And all of these electrons, they're all entangled with each other. They're all correlated. And let's say we need just one, I don't know, 1 bit per electron. Somehow it's not. I mean, it's not how it works. But let's just say we need 1 bit. Then we need 2 to the n electrons bits to store just the information for a molecule like this. And if you have 1,000 electrons, then it's 2 to 1,000, and the universe isn't big enough to store 1 to the 1,000 states classically, but it is big enough to store 1 to the 1,000 states using qubits. As a matter of fact, it's already doing it. The molecule exists. So the problem here, go back to our problem, the problem statement is, how do molecules bond? We have a very small molecule, this is CO2, and we have a very big molecule, which is the filter. And we want to know how well this filter will work as a CO2 filter. As I said, classically, this is intractable. Electrons are entangled, requires exponentially larger resources to simulate. But qubits can be entangled too. So they have the same properties as electrons. And this gets us back to what I was saying. Nature is quantum. We need quantum computers. And here, quantum computers actually solve this problem. And beyond this problem of carbon capture, in quantum chemistry, we can do quantum simulations that will impact drug discovery, protein modeling, material sciences, and so on. Just to develop a bit on drug discovery, a large amount of money is spent on simulations. Simulations are performed a long time on very big supercomputers that will consume large amounts of energy. Actually, they consume about the same as a small town. Quantum computers produce all of these, and hopefully down the line reduce even the cost of drug development. Now we've seen what quantum computers can do. Let's actually see quantum computers, or at least pictures of them. Now, if you type quantum computer on Google, this is what we'll end up with most probably. This is not a quantum computer, this is a fridge. That's a refrigerator. It's a very good and very expensive refrigerator, but it just cools down stuff. Quantum computers are very small. They're as small as your CPU, more or less. And this is, I think, either from IBM or Google. And all of this tubing, all of this device is just a dilution refrigerator, and it's there to cool down a small chip with the quantum device to temperatures down to something of the order of the 1 to 10 millikelvin for this kind of technology. Now, speaking of technologies, quantum computers, this is also a difference between quantum computers and classical computers. We're not sure yet which technology is the best for quantum computers. Today, for classical computers, it's pretty much settled. It's based on transistors and semiconductors. For quantum computers, it's not that clear. So this picture, I want to get back to it. This is used to cool down superconducting qubits, which we can see here. So this is now this is from IBM. This is a 4-qubit device. So it's basically a very small electrical circuit that is printed on superconducting material. So it will behave quantumly at low enough temperatures. And this is how they get the quantum behavior that they will use to implement qubits. IBM today, they have a 400 something qubit device that is online, accessible through the cloud for quite a lot of money, but still, I mean, it's accessible if you have that amount of money. We'll have others, I think 800, and they will double or more or less double each year. So this is how they look like. This is superconducting qubits. They have advantages. They use more or less the same techniques as that are used to fabricate classical computers. So you have material and you're printing your circuit. So it's, let's say, quote unquote, easy to fabricate. One of the downsides is that it works at cryogenic temperatures, so it needs these to be cooled down in order to operate. The qubits, since they are man-made, they're fabricated, they will not be exactly the same. So you have to take these small differences into account. And yeah, this is one type of qubits. The other, or let's say 2 other types of qubits are atoms. They are quantum systems, and we can use any quantum system as a qubit. I've put together trapped ions and neutral atoms in one category because they use the atom as the basis for qubit. In this picture here, we see a trapped ion chip. This is from IonQ. IonQ are a company that makes quantum computers, and this is one of their devices. And if you look closely here, this blue line is made of dots, and each dot is an atom. It's an ion, or an atom with one electron stripped away. So it has a charge. And one of the advantages of this technology is that this is not superconducting. They do not need these dilution refrigerators, these ones. Also, another advantage is that since they use atoms are all the same. So you don't have to keep track of each qubit and calculate your systems to correct for fabrication defects. Atoms, they're not fabricated, they're natural, so we can use them directly. The other thing is that they can all be connected together, and this is a point. Maybe I'll spend a minute on it. Let's go back to classical computing. You take a bit. What can you do to it? Well, you can apply some what we call logic gates. Invert it. You can apply NOT gate, for example. Now take two bits. What you can do with 2 bits, well, you can add them together, for example, and perform a bunch of 2-bit operations. Same goes with bits. It's just you just do the same thing, but there's the quantum version. Now, if you look at the left here, probably these two qubits here, which are facing each other, are not connected together. So you cannot directly perform some two-qubit operation. So you have to go through a third qubit in between, which adds one operation. And adding one operation is expensive in quantum computing, mainly because of noise, and we will see that later. With trapped ions, you can just physically move two ions close together, perform your two-qubit operations, and then get them back to where they were. Of course, it has also some downsides. It's very hard to control and to trap a large number of ions. So superconducting qubits today have a lot of qubits than trapped ions or neutral atoms. Trapped ions, they're also electrically charged, so they will interact with each other a lot. And we don't want that. We want them to interact when we want them to interact, but not on their own. They will also interact with the environment. And so, again, we have advantages and disadvantages to this technology. Neutral atoms, they work in similar way, but neutral atoms are states are neutral, so no electric charge. But what we need, or how we control them, is we control them via lasers. And now, again, you see the issue is that you get an advantage where you don't have the electric charge, so they don't interact a lot with each other. But they need a lot of lasers. You basically need 6 lasers for each neutral atom. And if you want to control, I don't know, 1 million qubits, that's going to be very difficult. Another platform for quantum computing is photonic quantum computing. And now here we use photons. This picture is a chip from a company. I think it's a Dutch company called Quix, and they fabricate quantum computers based on photons. Now, photons, again, they have advantages, disadvantages. The advantages of photons is that they don't interact a lot with the environment. They don't need this cryogenic cooling. But photons, they don't stay in peace. They just they move at the speed of light. So once you start computation, basically it ends immediately, and you have to figure out some computation scheme to perform some meaningful quantum computation. Here's another quantum computing platform, and I don't have a picture for this. And the reason is very simple, is that it doesn't exist yet. It's called the topological quantum computing. So we talk about topological qubits. I've named a few companies, Google, IBM, some others. You may be wondering, where's Microsoft? Microsoft is working on this. Now, topological quantum computing is something that will happen or we hope that will happen in the very long term. And if it happens, basically it solves most of the problems that I've stated before. So it's the holy grail of quantum computing in a sense. What I've put here instead is some code, or a screenshot of some code, and the result from a package called CQSIM, or Topological Quantum Simulator, that we have been developing at CQ Tech. We started as a research group working on topological quantum computing specifically before creating this CQ Tech group. And the idea behind topological qubits is that you've seen with photonics and even with these 3 technologies, that we store quantum information on individual particles or some individual systems. So, and individual systems, they're very to perturb. So the environment, let's think of the environment as this evil adversary which tries to mess with our quantum information. The environment will not have to spend a lot of energy to change the quantum information. So in topological quantum computing, what we do is that instead of storing the information on local particles or locally, we spread the information over a topological material. So if you want to change the quantum information, you'd have to spend a lot of energy to change the property of old quantum material. And we can actually see here this colorful braid. These are actually 4 quasi-particles called anyons. They have dimensions. And the way we do computations on them is that, first of all, we do not store information or qubits on anyons, but on a collection of anyons. And then to change this information in a meaningful way, that is, we are doing some quantum computation, but we just exchange these in some way. And this is what this braid is showing us. So we're doing the first pair twice, and then the second pair 6 times, and same with the third pair, and so on. And at the end, by exchanging these particles around, and this is a property again of quantum mechanics, that the path that the particle takes affects its state. Just by exchanging these particles around, when we fuse them back together, we find a different quantum state than the one we started with. So we can use this for computation. And again, this is a package. You can find it on GitHub or no. Yeah, you can just find it on GitHub. Just type TQSIM. Okay, so we've seen 4, 5 technologies. 4 of them are currently implemented, except for the topological one again. Now, what's the state of quantum today, or what's the state of computers today? So let's look at qubits. First of all, they are noisy, and this is what I've been talking about, or I just very briefly mentioned, that qubits today, they're very susceptible to noise from the environment, and they also interact between themselves. So they lose information quickly, which means that if you want to perform quantum computation on today's quantum computers, you have to be quick. You can't just execute a very big quantum program. It has to be short. It actually has to be shorter than the time it takes for the environment to mess with our quantum information. And this time is, depending on the technology, it goes from nanoseconds to microseconds, to actually maybe even milliseconds and seconds for neutral atoms. The other thing is that we don't have that many qubits on each chip. So for now, tens to even thousands of qubits per device. It's still very hard, or it's still a challenge to manufacture devices with millions of qubits, which is maybe the minimum of number of qubits that we're going to need for any meaningful quantum computation. And the reasons here, there is not just one single reason for all the technologies. It just really depends on the type of technologies. For example, I don't know, trapped ions. You cannot have, for now, millions of trapped ions, because I mean, how are you going to control million individual atoms precisely? And atoms, you know, that if you don't keep them there, if you don't control them, they will fly away. You will lose your qubits. So we will shorten that, or let's say we will take this noise problem, and then the problem of and we've put them in a term which you will find in the literature. It's called the NISQ era, or the noisy intermediate scale quantum era. So we have noisy qubits. We have not just 1 or 2 qubits, but we have, you know, tens to thousands. So it's an intermediate quantum era. So this is the NISQ era. What this means is that with today's computers, we are limited in the number of qubits we can use, and we're also limited in the computation time. So given a quantum program, first of all, you cannot use a lot of qubits. You're restricted by the hardware, but you also must finish your computation before your qubits lose their desired state. Now, to overcome these limitations, because we have these limitations, okay, but maybe we can do something useful with today's quantum computers. Probably we can, maybe we can. We have these algorithms which are hybrid, so they are half classical, half quantum, and so they do not have to run for a long time on a quantum computer. So just the quantum part, or just some part of the algorithm, is being run on a quantum device. So we only perform part of the algorithm on a quantum computer. There is some possibility, and this is at this point, some people will agree, or some people will disagree, but we may have a quantum advantage with today's quantum computers, or with NISQ era devices. We did not see this quantum advantage yet, but there is a possibility, and the best candidate are these hybrid classical quantum algorithms. The issue is that since we have noise, these algorithms will always require processing to deal with this noise. So once you make a computation, you do not trust the result of the computation. You will have to do it many times and then sort of characterize the sort of noise that we have in order to remove it from the result and have some less noisy result. As I said, no proven quantum advantage as of yet. Every now and then you will see either IBM, Google, or somebody else publish a paper saying, oh, we have some quantum advantage. We have performed the computation that would have taken computers maybe 10,000 years. But there is a pattern that keeps repeating, is that every time somebody makes this claim, a month or some team somewhere around the world will come up with a better classical algorithm and even beat the quantum approach using just a simple laptop. Okay, it happened and probably will happen again. So no quantum advantage as of yet, but all this effort is extremely useful for quantum computing research and development. We will never get a good or useful quantum computer if we do not go through these steps first. And speaking of these NISQ steps, here's maybe the most important slide in this talk. This is an actual result from an actual quantum computer. It's an IBM quantum computer that we have used for one of our on works at CQTech. So the top left here, we have a molecule. It's a beryllium BeH2, one beryllium atom, two hydrogen atoms. It has a very nice linear structure. So we have a hydrogen here, beryllium here, another hydrogen here. They are at their equilibrium bond distance. That is, they will not move around. If they are put at this distance, it's 1.33 angstrom. I mean, yes, it's 1.33. And now is to try to find the energy state of this molecule. That is, if I were to change the distance, would I have a higher or lower energy? And what does this mean is that if I try and compute the energy for every distance in a certain range, then I will have a certain minimum, and this minimum will correspond to the equilibrium geometry of this of our molecule. Now, this is not a very complicated molecule, but it's just let's say rich enough to be interesting to explore. It has 6 electrons. Yes, 4 electrons from the beryllium atom, 1 from the hydrogen, from the other hydrogen. So we have, let's say, 2 to the 6, or some exponential to the power of 6 of possible states that these electrons can be in. And this is showed here in the lower left. Here we just show the valence electrons and how they are arranged in the molecule, and they will interact in certain manner such that they will either break apart the molecule or keep it stable. And this is a very famous problem in quantum chemistry. It's actually quantum chemistry always starts with computing these energy levels, and the idea is to use quantum devices, today's quantum devices, with a hybrid algorithm, called the variational quantum eigensolver, or the VQE, to produce better or more accurate energy levels than what we have with today's classical computers. And believe it or not, even such a seemingly simple problem with just a few electrons is extremely hard to solve exactly, or let's say up to a very good with classical computers. So what we always make some approximations in order to simplify the problem and solve it, but that comes at the cost of a lower accuracy. On the right here, we can see the algorithm, or the results from this quantum algorithm, the VQE, that we have run on what they call the BELEM quantum device at IBM. It has 5 qubits. We only needed 4. So this algorithm is an algorithm. It just tries some parameters, measures the energy, and then gives the energy to the classical computer, which will decide and say, okay, now let's try this set of parameters. It's a bit like machine learning, and actually this is part of what we call quantum machine learning, but that's something else. And then as your algorithm keeps iterating through more and more parameters, it converges towards the desired energy state or value. For the BH2 molecule, it's around minus 15.6. Here you can see that you are not exactly there. There is some difference. That's some error. But again, this algorithm is the very simple algorithm with no post-processing for noise or anything, and there is no optimization. And it's run on a quote-unquote bad quantum device. But still, we do get some meaningful results. So we know that quantum computers today, they do give some results, but they are not yet better than classical computers. Right. So I've given what I think is an overview of quantum computing, starting from qubits, what they are used for. We've seen some pictures of quantum computers, and we've seen this last slide, which actually shows an actual real quantum computation made on a real quantum computer. What to take away from this talk? Well, quantum computing is not a luxury technology. It's a necessary technology. Again, it comes down to the fact that nature is quantum, you need quantum computers. Our classical computers, as powerful as they are, as powerful as they may be in nature, they are physically limited. They are mathematically, they are completely equivalent to quantum computers, but they will not solve the same problems in the same amount of time. And we do not want to solve a problem in a million years. We want to solve the problem in, I don't know, days at most. So quantum computing is necessary. If we get some or start getting some meaningful results from quantum computers, then this will enable huge technical leaps, and this will be in various fields. We've seen quantum chemistry, we've seen logistics. So if you can find accurate energy levels, let's say for a big molecule, or like we've seen with the molecule from the Deloitte challenge, then this will enable finding, I don't know, better drugs faster and cheaper, finding better battery technologies, going back to the optimization problems, having a better scheduling of fleets of trucks and trains and so on. So it will enable, or it will have a huge benefit in various technological fields. The third point is a bit, let's say, non-technical. Quantum computers do exist, and you can meet some people, and I'm not talking about the average layperson, but even some scientists today think that quantum computers are still just a theoretical field. I mean, we've seen here there is a result from a real quantum computer. So quantum computers do exist, for those of you who still don't know. To talk to the other extreme, they are not useful yet. Okay, we do not have some quantum computer that is better than current classical supercomputers. They are not useful yet for the reason I've described earlier of noise and the number of qubits and so on. On the fields of quantum technologies in general, a significant amount of effort and funding is being spent on or for the development of such technologies. Maybe not by everyone, but by most of, if not all, advanced countries: the US, Europe, China, Japan. South Africa has a national quantum computing initiative. So does India, by the way. So a lot of effort. It's a nascent field, but it's also a very active field. It's also a multidisciplinary field. So even if you're not an expert on quantum computing, you can contribute to it. I mean, you've seen that the wide range of technologies that are used: superconducting materials, electronics, optics, computer science. All of these fields are needed for development of quantum computing. So whatever your field of study or work is, you can absolutely contribute to it. And maybe I will end up with a slight warning: do not fall for hype. There is a hype around quantum technologies and quantum computing these days, where people are creating startups and they're promising impossible things. Well, this is good for them. This brings them investments and money, but this is not for the whole computing development and the whole ecosystem, because it will crash, just like the internet bubble crashed in the early 2000s with the dot-com bubble. Companies promising impossible technologies, and then at the end people realized that this was not going to be a thing, even though internet, we know how useful it is today. So something similar may happen to quantum computing. So let's not fall for the quantum hype. Let's know what quantum computers can and can't do. Let's know where classical computers are better and where quantum computers are better. And to learn about what quantum computers can and can't do, I will just give a few, let's say, starting points for those of you who want to start in this field. I recommend the courses by QWorld. It's an international not-for-profit organization. They have some of the best beginner courses on quantum computers. So just type in QWorld and then look at the courses. Actually, we did deliver a course on topological quantum computer with them. So they're focused on teaching and also on research. They do have some research programs every year. And IBM, they have their many of their quantum computers online. Some of them are free. You can just create an account and start coding and start playing around with them. They also offer beginner to intermediate courses all year round. So I think every basically there is these days, actually this week or the week before, there is this Qiskit Quantum Summer School, where you learn the basics of quantum computing and then you go to some intermediate level. You can just start by learning how to program quantum computers. I mean, at the end of the day, when you're using or when you learn to use your classical computer, you did not have to learn about all of the electronics and all of the, actually there is some quantum mechanics there. You just started playing with computers and using them. You can do the same with computers. You can just immediately start learning quantum computing languages and frameworks like Qiskit and PennyLane and Cirq. So Qiskit, PennyLane is from Xanadu. It's a quantum computing company in Canada. They are based on photonics. Cirq is by Google, and there are many others that you can find. And actually, they all come with courses. So you can just go to their websites, see how to install these SDK, start working with them and use courses. And of course, don't miss events online, events like this one. There are dozens, probably, especially in the summer, where there are each week. But you will find them also year round. And yeah, with this, I will just end with some links and contacts. You can join us on a Discord server we've launched a couple of months ago. This is the link. I will share these slides with you, and they will also share the link with you. It's called Quantum. For now, it's private, but we will make it public once we get the core of active participants there. So it's a space for not just Algerians, but to discuss quantum technologies in Algeria, and also get people or get some Algerians to know quantum computing. About our group, you can find us on LinkedIn. Just type or you can email us at contact@cqtech.org, or go to our website cqtech.org just to see what you're working on. And if you want to collaborate, we also would love to collaborate with you. And with this, I will just thank you for your attention.
صحيت ناصر، بريزونطاسيون في القمة. شوفوا إذا كاين ناس هنا في الأودينس عندهم دي كيسيون ولا في لي كومون اللي عنده كيسيون يدير ريز هاند بيهضر. سينو إذا صالح إذا كاين ناس في اللايف تاع فيسبوك عم يسقسوا. أوكي أيوب تفضل. أيوب ما نش سمعوا فيك إذا تهضر. مازال ما نسمعوا فيك. اكتب الكيسيون تاعك في الشات إذا ما قدرش تريقلها. بون ما يسمعوا فيه بالك دوك يكتب الكيسيون تاعو في الشات نشوفوا.
Not problem.
أنا سمعوا فيك واقع هكا. أيوب عاود هذر. لا بون صالح إذا عندك كيسي.
ممكن عندي سؤال متعلق بالكوانتم كيمستري ولا دونك البروبلم اللي عطيته. ما نسقسيك بلونجلي بس عندي زميل تاعي هنايا باش يفهمنيت.
Yes.
Donc, when you mentioned the quantum chemistry problem with the different molecules, etc., you mentioned that the classic computer are limited since the electrons are entangled. And then you mentioned that qubits are entangled too, therefore quantum computers can handle this problem. What is the
Yes.
relationship between, let's say, the problem and then the use of quantum computers related to that sort of problem?
Yes, actually, this very problem is what motivates quantum computers. So when we have systems that are highly entangled, what do we mean? We mean that two things that are entangled when they evolve in a correlated. So if you were to do this with classical computers, you would have to represent systems and then also have some separate program that keeps track of all the possible correlations. And possible correlations, they grow exponentially in the number of parts that you have in your system. So a highly entangled system like this one would take, I mean, you let's say you have 1,000 electrons again. You would need 1,000 states to represent the electrons, but then you would need to the 1,000 states to represent all of the correlations, to keep track of them. And as the universe, or at least the visible universe, is not big enough to store this amount of information. However, qubits, they can do this without external help. We can entangle them. So if we have 1,000, I don't know, states, and let's say we can represent them with 1,000 qubits, then we just need the 1,000 qubits. We do not need extra. We do not need extra space, extra time to deal with all of the entanglements. So to answer your question, qubits being able to be entangled, or let's say not reduced, but is enough to represent all of the correlations we need for extra work. It would be impossible to do with classical computers. I hope I answered the question.
Yeah, thank you very much. Yeah, pretty much clear. Yeah, thank you very much.
فولو اب برك وبعد أيوب يسقسي كيسيون تاعو. تما في هذا السونس شغل ما كدير عفسه بين سيميلاسيون و اكسبيريونس في نفس الوقت، باسكو الكيوبيت عندها نفس البروبرتي تاع تاع الالكترونز، تما في بلاصه باش دير سيميلاسيون باش سيميلي هذا الموليكول اللي فيه الكترونز تيوتيليزي كيوبيتس اللي عندهم نفس لي بروبرتي تاع لي زيليكترون.
Exact.
اوكي تما معناتها شغل ماهيش سيميلاسيون في السونس كلاسيك تاع سيميلاسيون.
It's still a simulation, but it's a far more efficient simulation.
سيميلاسيون بصح ماهيش شغل ماهيش 100% computational. كاين بروبرتي تاع الماتير.
For example, entanglement is not simulated; it's real.
فوالا جوستوم.
Yeah.
اوكي. ايوب سقسي كيستيون.
تست كاين اوديو.
انا نسمعوا فيك.
خلاص. لا كيستيون اللي سقسيتها في الشات، اذا لي ليميتاسيون اللي راهم كاين دوكا في الكوانتم كومبيوتينغ راهم يعني ناقصين انجينيرينغ، ولا اسكو لي ليميتاسيون راهم اكثر في الكوتي فاندامنتال ساينس؟
It's mostly, if not entirely, engineering problems. It's fundamental science, using already existing science, even to simulate possible quantum tests. So for now, we don't have an issue with the fundamental science or the theory, but it's an engineering problem more. Maybe if we discover some, let's say, fundamental theory that will help us make better quantum computers, okay, that's a possibility. But as far as I know, it's just engineering issues.
اوكي.
ياسر خالد.
السلام عليكم.
عليكم
انا
السلام.
نسمع فيك. عليكم السلام.
راكم تسمعوني مليح؟
ايه انا نسمع فيك.
كونيكسيون راه شويه قليله. عندي سؤال فيما يخص prerequisite subjects to tackle quantum computing. الأخ ناصر هو درس في جامعة قسنطينة يعرف Yes, that's my question.
No, yes, thank you. So, okay, let me go back now. Mentioned keyword, IBMs. These, if you want to get started with them, you need high school level physics, high school level mathematics. Basically, that's it. And the keyword courses specifically are designed for fresh first-year computer science students that do not even know about complex numbers. So whatever your level is, you can just pick a course and start from it. Ideally, what you want to have is at least some knowledge on matrix multiplication, complex numbers, and some programming, preferably Python, because nearly all the content programming SDKs are written in Python. So this is a big plus if you have knowledge on linear algebra, so matrix multiplication and vectors and so on, complex numbers, and some level of programming, preferably Python. But if you don't, with these courses, just high school level physics, high school level mathematics should be enough.
I am more interested in the theoretical side behind quantum computing. Can you
Yes, okay.
direct me there?
Okay, so theoretical side, okay, there are many theoretical sides to quantum computing. Some of them would require information theory.
You
all
mean
of them.
quantum information theory?
No, just classical information theory or probabilities even.
Okay.
I mean, again, it depends on which theoretical side you want to tackle. There are, for example, theoretical works on the hardware. There are theoretical works on the algorithms, which would, for example, much more mathematics than physics. The hardware needs a lot more physics. Yes, there are some good in between.
I am more interested in the mathematical framework of quantum computing.
Okay, for mathematical framework, you very probably need, let's say, a solid grasp of probabilities. And the reason is that quantum probabilities don't work in the same way as classical probabilities. And linear algebra is a must for this. So at least linear algebra, I would say.
Okay, thank you.
Also, I wanted to add something to what Nacer said, if I might. Are you hearing me or not?
Yes.
For Khaled, who asked about prerequisites, in Q. Brown's first introduction to quantum computing, they even have a module named Q Prep, which is for people that haven't even graduated high school. It teaches you in Python, linear algebra, and complex numbers specifically. Also, I'm currently participating in the Qiskit Global Summer School for 2023, and it's like every other Qiskit Global Summer School. It's back to basics. Last week, they actually started teaching us about operators and basic linear algebra stuff. So at the moment, every course is starting from basics and is open for non-physicists, also people with computer science background, people with data science background, with practically any background, just a grasp of some simple mathematics. And they can even teach you some linear algebra, and you can get started in quantum computing. And then to get to the theoretical framework or to the algorithms and everything, that you need some more specific stuff. But you can, the more you get into the field, the more you see exactly what you need, and you see exactly what you already have as material to attack that field.
سؤال تاعي كان الأخ ناصر على specific stuff، باسكو أنا طالب دكتوراه فيزياء نظرية في جامعة وهران، دوك راني نحوس على السبيسيفيكس. ربي سألتك سؤال، باسكو حنايا في الجامعة تاعنا تركيز كان كتر على الديفيرنشال جيومتري، جنرال ريلاتيفيتي، قرينا الكوانتم ثيوري فما قريناش كوانتم انفورميشن ثيوري. بغيت نعرف شحال تلعب دور باش نقدر نتعلم شوية في الكوانتم كومبيوتينغ.
There are some direct applications of, you mentioned differential geometry. We worked on a problem. Mohiman was with us, and he actually did a very good job on this. It was on the thing we saw here, the variational quantum eigensolve. So this is, since you had the theoretical physics background, this is the variational principle, the Reed's theorem. And then in order to make it run faster, you can use some theories and notions from differential geometry. So you can always find applications of whatever your field is in quantum computing, because again, quantum computing is designed to solve a wide range of problems.
اوكي، نشكر الاخ ناصر على المعلومات. كونكسيون عندي راه كاع عيانه، دي فوا الهضره تتقطع.
صحيت ياسر. لا كان سؤال.
Yes, sir. You can contact us. بعد نبعت لي زيميل و you can just send your questions and we will try to answer in the best way.
ما كاش مشكل. اوكي. I joined assembly for this kind of conversations.
صالح كاين دي كيسيون في اللايف؟
لا ما كاش دي كيسيون في اللايف.
اوكي تسمى اذا ما كاش شكرا ناصر على التولك تاع اليوم، والسمانه الجايه ان شاء الله عندنا لقاء مع بروف طاهر وابح اللي راح يحكي لنا على تجربة البحث العلمي في الجزائر، بيئة البحث العلمي في الجزائر، وما كيفاش جابوا جرانت ثم تقدر تقدر تمول البحث تاعك بمنح خارجية. تلاقاو السمانة الجاية إن شاء الله.
اسمح لي ندير دقيقة.
وي
مازال كاين شوية وقت.
وي
لو كان تعاود تولي لهذيك السلايد تاع الكوانتم كيمستري. باك خممت هذه كيفاش تقدر تستوري الانفورميشن بهذاك الليميتد نمبر اوف كيوبيتس.
تقدر تعاود which information؟
الانفورميشن على الموليكيولز كي يكبروا.
So okay, so it's field in itself. It's called we start Hamiltonian actually. So what we actually deal with is the Hamiltonian that describes this system. So this Hamiltonian comes from basically field theory, where you have what we call creation and annihilation operators. And these operators, what they do is that, let's say, they move an electron from one orbital to another, or then move it down, or move two electrons at the same time, and so on. And then what we do is that we these operators, and then we perform a mapping, and we map them into Pauli operators, which are basically quantum operators on the quantum device. So the way we store information is basically we start from the Hamiltonian, we express the Hamiltonian for our problem, then we perform this mapping, and then we end up with some operators that describe the Hamiltonian. And then these operators, they will operate on a set of qubits. And then these are the qubits that we start with. So we start with all 0 qubits, and then we perform operations on them. The operations are obtained in the mapping from Hamiltonian, or let's say, yes, from the Hamiltonian with creation annihilation operators to a Hamiltonian with what we call Pauli operators. I don't know if you follow, I don't know what your background exactly.
يعني قريتها كي كنت درستي RB. mais quand même راح يكون عندنا the same number of Pauli operators as we have electrons في الحالة.
No, not necessarily. It doesn't follow the electrons. It follows the orbitals. It creates and annihilates an electron on an orbital.
On an orbital.
Yes. And then the question is, how many orbitals do you consider?
Yes.
And this, it's up to you. You can approximate. You can leave the full problem. It depends on also how many qubits you have. So sometimes you need to approximate. But in the long term, we don't want to approximate. We want to have enough qubits to represent all of the relevant orbitals.
Okay. If the problem is too large, what do you do?
I'm sorry, what's too large?
The problem, you don't have enough qubits.
Yes. So for now, all the problems are too large. We don't have enough qubits to represent even this. This would need, if we don't use any approximations, it would need I forgot the number, maybe 12 or more qubits. Although we do have 12 qubits, but 12 qubits, this also introduces a lot of noise. So effectively, we only have maybe, I don't know, 6 or 8 qubits. So what we do is that we make some approximations. We say, okay, let's say that I don't know if you see my mouse, but here the bottom left figure, the topmost.
Yeah.
Okay, so the topmost orbitals, we can say that they don't contribute that much to the dynamics, and then the core orbitals, we also say that maybe they do not contribute that much. So we discard them, and then we reduce the number of orbitals, thus reducing the number of needed qubits.
But is there a way to circumvent the issue of missing qubits? So you simplify the problem. Take, for example, you have a protein, right? No matter how much you're going to simplify it, there is no quantum computer out there that has enough qubits for it, for a protein. So are there ways? So I don't know.
For now, okay, I think I got the question. So yes, if you go back all the way here, yes, for now, we have to simplify the problem. I mean, if there were ways that we could reduce the number of necessary qubits and solve the same problem, that would be an amazing Nobel Prize winning, I don't know, world changing result. But for now, we don't. So that's the thing. That's why we say we are here in the NISQ era. This intermediate scale is what us in the number of qubits. But on the long run, we should not be limited by the number of qubits. Just like today with classical computers, we are not really limited in the number of classical bits for classically tractable problems.
When also, so I might want to add something that I read this week. One of the applications when dealing with proteins, well, for the moment, we don't have any quantum computer that is close to treating an actual protein that is a human protein, which is the order of 100 or more molecules at least. One of the ideas that is actually being used in quantum computers now, it is to solve for the protein fold. The protein is composed of amino acids. We actually just solve for the optimal three-dimensional arrangement of those amino acids. So this is one step closer. And then you start, maybe you can approximate. It depends on your approximation. You start to dissect the problem. For example, you find the optimal fold, and then you say, okay, this is how the fold is gonna be. Now let's consider the interactions between amino acid, isolating it. Okay, the only one that are connected together are the one that are gonna be in the interaction. The further one are not gonna be there. Maybe you can simulate that part on a quantum computer and you dissect the problem. But it's all about approximations and how much it can deviate you from the reality. If we don't consider approximation, technically we can simulate any quantum system. If it has 1,000 states, we can ignore 999 and simulate it on 1 qubit. So it's doable if you approximate. It depends on how much, how far are our approximation taken us from the real solution.
Can we
yes, exactly. So as long as we're in the intermediate scale, we have approximations. But let's say what we call the fault-tolerant quantum computers, maybe, I don't know, 10, 30 years from now, we should not need these kind of approximations. We can just input the whole protein, for example.
Can't we simulate it piecewise and then find a way to mix them using maybe a classical computer in the end?
Yes, you can, but this will amount ultimately to something close to classical simulation, because then if you simulate piecewise, then what you're doing is that effectively you're reducing the amount of allowed entanglement. Let's say you simulate one amino acid and then the other amino acid, but you don't simulate both amino acids. I mean, the whole is more than the sum of the parts, basically, here.
Yeah.
So, yes.
Okay. Thank you.
ياسر عنده كويستيون نورمالمون.
عندي سؤال على topological quantum computing.
طيب.
اسكو أنا اللي نعرف على الكوانتم كمبيوتر they need to work at a very low temperature like near absolute zero. Is that a
Depend-
problem in topological
depends
quantum
on-
computing?
Sorry, depends on technologies. The quantum computers in general, they are not restricted by the temperature, but it's the technology. So quantum computers, because superconductors, as of yet, there is a whole discussion and going on right now on room temperature superconductors, but today's proven superconductors, they need cryogenic temperatures. This is why we need cryogenic temperatures for quantum computers. There's also the issue of noise. To reduce noise, we need lower temperatures. For topological quantum computers, there are, for now, ways to achieve a topological qubit. One is to actually make these quasi-particles called anyons. And these anyons, this is the approach that Microsoft is taking. And these anyons, they need to operate at cryogenic temperatures. So because they use superconducting materials. There is another company, it's called Quantinium, which Idris I think very well. They have an ion, so they don't need cryogenic temperatures, and they did quantumly simulate anyons using ions, so using atoms basically. And this also is equivalent to having the real anyons, and if they had a larger ion trap device with a low, or let's high resilience to noise, then they would also be able to create a topological computer without the need for a big dilution refrigerator. So two approaches. One of them needs cryogenic temperatures, and one doesn't.
اوكي شكرا.
You're welcome.
صحيح ناصر. كيسيون واحدة أخرى. المهم كما قلنا ناصر صحيت على التولك وعلى لي كيسيون على التفاعل، كان بزاف انتيريسون. أسامة. نعم أسامة سقس. ماشي نسمعوا فيك أسامة.
تسمع؟
كان يسمعوا.
اوكي يعطيك الصحة ناصر. ديزولي ما نقدرش نهضر اكثر، مي جيست حبيت نذكر ثاني بور لا سيمين بروجين ان شاء الله راح يكون بروفيسور طاهر وابح اللي يخدم اللي ناصر يخدم معاه في الميم جروب، راح يحكي لنا اكثر على الكوانتم انفورميشن دومين وعلى كامل واش راهم يديروا لي زوبورتونيتي راح يكونوا وليكسبيريونس ديالو. دونك ماذا بينا اللي يحب ليا وانتيريسي بهذا الدومين مليح يحضر ثاني لا سيمين بروجين ان شاء الله.
اوكي مع السنة الجاية مع بروفيسور طاهر وابح على البحث على بيئة البحث العلمي في الجزائر اون جينيرال. وصحت ناصر مرة أخرى، تلاقاو السنة الجاية.
الله يسلمك.